The life cycle of a medium-mass star. The Sun is the largest and the most massive object in the solar system, but it is just a medium-sized star among the hundreds of billions of stars in the Milky Way galaxy. Medium-mass stars are those that spend their dying years as neutron stars. Scientists have observed this category to have a lower limit of just above 1.4 solar masses and an upper limit in the neighborhood of 3.2 solar masses. Any star's life cycle begins as a nebula. Nebulae are usually made of gas, dust, hydrogen, helium, and other ionized gases. The size of a star is determined by how much matter is available in its parent nebula. This cloud of dust and gas begins to collapse upon itself due to gravity, forming an increasingly hot, bright, dense mass at its center. This is called a protostar. During the protostar stage, gravitational contraction continues, slowly at first and then much more rapidly. This collapse causes the core of the developing star to heat much faster than its outer envelope. When the core reaches a temperature of 10 million Kelvin, the pressure within is so intense that groups of 4 hydrogen nuclei fuse into a single helium nucleus. This nuclear reaction in which hydrogen nuclei are fused into helium is known as hydrogen fusion. When the protostar is sufficiently hot and dense, the process of hydrogen fusion begins taking place in its core. Fusion produces enough radiation pressure to counteract the force of gravity, and gravitational collapse ceases. The protostar has become an actual star in its main sequence phase. The star will spend the bulk of its lifespan in this period of stability, generating light and heat from the fusion of hydrogen into helium for millions of years. During the main sequence stage, stars experience minimal changes in size or energy output. Hydrogen is continually being converted into helium, and the energy released maintains the gas pressure sufficiently high to prevent gravitational collapse. When the star's core runs out of hydrogen, gravity has its way once more. That is, until temperatures rise high enough to allow helium fusion, which produces the outward pressure needed to stabilize things. When no helium is left, the cycle begins again. The core thus oscillates between states of compression and equilibrium as increasingly high temperature fusion reactions take place. Meanwhile, the extreme heat causes the star's outer layer or shell to expand to a radius comparable to that of the Earth's orbit. At such a great distance from the core, the shell will cool down enough to turn red. The star is now a red giant. Nuclear reactions cease forever when the star's core is reduced to iron. That element will not fuse without additional energy supplies. Gravitational collapse resumes catastrophically with a force strong enough to destroy the very nuclei of the atoms that make up the core. This generates so much energy that the explosion dominates the sky for light years in every direction. The star has gone supernova. The temperature of a supernova at its peak can reach up to 10 billion degrees Fahrenheit. Meanwhile, what's left of the star has shrunk to a diameter no larger than a few kilometers. This is about the size of a city. At this density, the outward pressure generated by protons and neutrons reacting to compression is finally sufficient to halt gravity. The star is so dense that, if you could bring a teaspoon of its matter to Earth, it would weigh 1 trillion tons. It rotates up to 30 times per second and exhibits a very large magnetic field. It is a neutron star, the final stage of a medium-sized star's life cycle.